Hi, welcome to the Signal Path. I have an exciting episode today because I have a good friend of mine, Timo, here, who's going to help me show you a project we've been working on actually quite a long time ago, and it's been sitting on my desk for some time. I'm talking about one of these RGB LED matrices which you can design a driver for, and then you can display whatever you want. And here we've made a clock that displays the time, kind of writes it out in words as opposed to in numbers, and it also has a date at the bottom. Now, you can buy these pretty easily nowadays. They're available on eBay and a bunch of other manufacturers, and they even give you the code for you to run it using an Arduino. But we thought, that's no fun, because if you do that, then you're just using someone else's code and someone else's algorithm. The best is to really develop an algorithm for yourself, because then you understand not only how this display works, but also have an opportunity to learn something completely different. So here, we're actually using an FPGA to do this. Now, I'm not an FPGA expert myself. Timo here has a PhD in electrical engineering. He's a DSP expert for optical communication. So to him, something like this is a child's play, basically. It took him 10 minutes, 15 minutes for us to come up with an idea, and then
maximum
of 10 minutes, and then spend a couple of hours here writing the FPGA code for it. And to make it even better, he's going to explain step by step exactly what his code does. He's developed a block diagram for you to show you how he thought about the problem and how he eventually came up with the display driver. So he's basically written something similar to a video card, which has a memory mapped component inside an FPGA, and he continues to write to the FPGA, handles all the communications that are necessary. So there's quite a bit of learning experience there that he's willing here to share with us. So I'm pretty happy to have him here, so don't forget to wait all the way to the end of the video to see every little bits and piece, and we're going to really dive into the detail and figure it out. Anything else you want to add?
Yeah, well, first, hello everybody. I'm pretty excited to be part of one of Shahriar's episodes, and it was a lot of fun doing that project together, so I'm excited to explain everything to you, and yeah, let's go straight into it.
Yeah, let's do it. And here is our RGB LED matrix, and right now it's programmed to display the time and the date. And of course, we are displaying the time by literally spelling it out. So right now it is at 10:48, and you can see the date at the bottom, and there's some counters in the corner, binary counters, to show the different frames arriving. Now, this is a fully wireless system, meaning that the only thing this board does is that it receives a frame of data from the computer through the Bluetooth, and then it displays it. So constructing this frame is actually done on the computer. Right now the MATLAB is running the algorithm to generate this face of this clock, so you can program any clock face that you want, and then it will be uploaded through the Bluetooth. Another advantage is that you can then have this display anything. If you wanted to receive updates or email notifications or anything you want, basically you can do it, because it has a complete wireless display to the computer. And if I go ahead and turn this around, you can see that we have our FPGA board, our Bluetooth RS-232 interface over there, and the display driver coming from the FPGA board, and all it needs is power. Everything else is handled through the Bluetooth interface. So this is in a way like a video card that receives a frame of information, and then it buffers it and then displays it continuously in the background. And of course the FPGA handles all of that. And we're going to go into the detail of showing you how that FPGA works, and Timo has written the algorithms for that, so he'll go through it. And I just wanted to take this apart a little bit more to show you the board, talk a little bit about it. Most of it is going to be focused on the FPGA algorithm, and at the end we'll load up some picture or something so you can see it display something else. But it's a really fun little project. It's a nice conversation piece, and because it's on this stand, you can just put it on your desk and write some software to communicate with it. It's a pretty fun little project. And here is the back of the RGB LED matrix. Unfortunately, I can't take the plexiglass off anymore because I've curled this cable and have soldered a power connector at the back of it, so I'm unfortunately at the end of the disassembly here. But you can easily find pictures of this, but I just wanted to give you a quick overview. Obviously this is our power cable that's going in there, and I'm holding this at an angle to avoid reflection, because you can see that it reflects everything. The power cable goes in, and directly in the middle it's screwed into the board. Now at the same time I'm also taking some power back out again in order to be able to run it directly to the FPGA board. So this allows me to just apply 5 volts in there, which then powers both the FPGA board as well as of course the board itself. Now the construction of the RGB LED matrix is really simple. It has row drivers that drive each individual row depending on which row is selected by a 4-bit address. And all of those are basically these ribbon cable interface here. You can see there is an in and an out. That's because these are supposed to be cascadable so that you can program multiple of them in a row from only one interface. This is very common for RGB LED matrices, that they all do this. You can see, I think, Pooch's reflection up there. There he is. Look at him. He's sitting there examining, making sure everything is going well down here. And so each individual IC driver that you see under the main big ICs on this side and this side are the ICs that drive each individual row of LEDs here. So there's 32 LEDs in there. That means that each of them is in red, green, and blue. So you're going to have that 3 times 32 constant current drivers. Now they use constant current drivers for LEDs as for obvious reasons, to make sure that the current through the LED is the same regardless of power supply variation between different panels, and that keeps the same brightness and therefore the same color. And that's really important. This is very common, of course. I'm sure you know about that. Now another thing they do is that they have a 4-bit address, and because they have a 4-bit address, well, obviously 4-bit doesn't cover 32 rows, it can only cover 16. So this display supports writing to 2 lines at a time. So you write these 2 lines and then you move to the next one, and then you move on to the next one, and you move to the next one, and all the way down by 16 you have written an entire frame. So you fill this and this half simultaneously. They do that so that you can achieve higher frame rate by essentially having to write only 16 rows as opposed to 32. Now there is another clever circuitry in there which I would just hint at so that you would keep it in mind. There's actually a rectifier circuit inside this, and that rectifier circuit is connected to the enable pins of all the drivers. If there is no address increments at a certain rate, meaning that if the address of the row increment isn't continuously changing, it would disable the screen. Now can you guess why they do that? Well, they do that because they want to make sure that if the address isn't advancing and this display is stuck at only displaying one row, it wouldn't be stuck showing that one row, because then it will have too much current and it will damage the LEDs. The current is higher than the steady state current the LEDs would require, because they expect this to have a continuous refresh rate. Therefore, they put more current to achieve higher brightness for shorter duration of time. And that's another thing that LED matrix of course do. So I recommend that you go into detail to take a look at this interface more, but not to worry, we're going to go into our own details showing the FPGA board. Timo is going to explain that thoroughly, and we're going to show you even the waveforms in simulation in FPGA, as well as the measured waveforms that we're feeding to these lines, which hopefully should be quite a bit of help if you're going to develop something like this. And our FPGA board is this FPGA board right here. It has a Spartan-6 on it. Of course, it doesn't matter what FPGA board you're using, because the logic, the algorithm is of course going to be all the same. And I'm using a simple Bluetooth RS-232 interface in there so that we can send our frames with RS-232 directly into the FPGA. So Bluetooth serial data comes in, goes into the FPGA. FPGA does this thing that we're going to explain, and it's going to generate the waveforms necessary to drive the display. And all of that is going to fit really nicely together, as you saw before. And you know, for our example, we had I've written a MATLAB interface that I just talked about, but you can write pretty much anything you want. So let's go and take a look at the FPGA implementation. Timo is going to explain that. Hopefully you'll find that useful as well.
So Shahriar explained the overall system and how everything is supposed to work. So now it's my turn, and we can take a look into what actually happens inside the FPGA and how do we connect the PC to the actual display. So here you can see a block diagram of what happens inside the FPGA. You can see there's kind of 3 major blocks. Let's look at the top block first. This is pretty much the clock control. So we receive a 32 megahertz clock. That's an onboard oscillator on the FPGA board. That clock we feed into a PLL that's inside the FPGA, and this is programmed to provide 2 different clocks. One is 14.77 megahertz, which we use for the RS-232 interface, and then a much faster clock, which is programmed to be 192 megahertz, which is close to the maximum clock frequency at which the FPGA can operate. So let's see how we get the data from the laptop into the display. Therefore, as Shahriar explained, we use the RS-232 interface to connect the PC to the FPGA. This is the block here on the left. This basically is just one single input, which is the RX data, which comes in at 115.2 kilobaud. The RS-232 interface is very simple. We just take the received data and feed it into an 8-bit shift register. Once the byte is complete, we can write everything in parallel into our RAM, and depending which color we received, the Uart controller will select the appropriate RAM that we want to write to, and that way, byte by byte, we can write the information of the display information into the FPGA.
So here you describe that the data coming in at 112 kilobaud is shifted into a shift register. But of course the FPGA is receiving a 14.77 megahertz clock. So how does the Uart know what baud rate to expect?
Well, you have to tell the FPGA what is the baud rate of the system. It has no way of automatically detecting it. But if you look at the clock frequency that we feed into the Uart portion of the FPGA, it's set to be 14.77 megahertz. If you do the math and you divide that by 128, you actually end up at pretty much exactly 115.2 kilohertz. So we're actually oversampling the input from the RS-232 interface by a factor of 128. So we're only kind of shifting data into our shift register every 128 clock cycles. So this is all handled by the Uart control, which does the counting and also controls, as I said, the write enable and the address counters when we receive the multiple bytes that make up one frame of the overall image that we want to project.
So let's talk about that framing. So we have 32 pixel by 32 pixel, that means 1024 pixels, and we are doing 8-bit colors, meaning that each red, green and blue LED has 8-bit levels of PWM on it, right? So that means every frame coming in is 1024 times 3 bytes of data. So I'm assuming that in order for you to distribute that data properly among the different RAM blocks, that's also handled by the Uart.
That's also handled by the Uart control. So one thing that we figured out throughout designing this is that the RS-232 interface is not perfect. There's bytes that can get lost.
It's mostly because of because we're using the Bluetooth converter.
That's either through Bluetooth or because there could be
missing bits and errors.
Other missing bits or errors or something. So one thing we've actually added to our frame is we made one single color illegal, which is the color or color value 1, and we've designated that value to be a reset. So now every time before we send a frame, we send a single byte containing the value 1, and then that will reset the counters in the Uart control so that we always keep sync with the computer. Otherwise, our picture on that we display could be somehow shifted, maybe one line down, or some weird distortions could get corrupted. So we need to keep sync, and so we have one sync symbol that's always inserted.
So if I can understand correctly, as the data comes in, the 1024 by 3 bytes data comes in. The data comes in, the Uart puts it into the shift register, grabs 1 byte at a time. The Uart control is keeping track of where you are in the frame. Data comes in, Uart control just says, okay, you're going into this one, the next one you're going to this one, and you're going to this one, and so on, and it starts continue filling these RAM blocks with knowing where in the frame you are. And then once it's done, 1024 by 3 comes in, all the memory is full, and then what happens?
Well, once the memory is full and we received one full frame, we have this single line here, the control going from the UART to the display controller. The UART informs the display controller that a full frame arrived and that it can start displaying it. So as Shahriar said, we have 1024 pixels times 8 byte times, or 8 byte each times 3 for the different colors. However, what we've done, because you don't want to update your frame while displaying it, that would, because the UART is very slow, you could actually see it on the display. So one thing we've done is we actually doubled the size of the RAM, so we can write one frame while displaying the other frame that's already fully stored in the memory. So we are actually, I mean, this can be implemented very easily just by flipping the most significant bit in the address. So if the UART is writing to the lower portion of the RAM, then the display controller reads from the upper portion of the RAM, and vice versa. And always the UART controller informs the display controller when to switch from the top half to the bottom half, and they kind of alternate, always one reading to a section while the other one is writing to a different section.
Right, so what you're saying is that each of these RAM blocks are actually twice as big as they need to be for a single frame, so that you always display a different frame than the frame you're writing to. And this will give you a smooth picture so that you don't see the frame being filled with UART data, because UART data is much slower than the frame rate you want to accomplish using the interface that we have. So now that we've reached this point, tell us a little bit about this entire section that controls the RGB LED matrix, and also explain why do we have 6 blocks of RAM here.
Alright, so let's look at the transition from the UART control to the display control portion of the FPGA. So one nice feature of the RAMs in the FPGA is that it's actually dual port RAMs, meaning you have 2 individual ports where you can write and read data that can operate at independent clock frequencies. That way we don't really have to worry about transitioning between different clock domains, because remember, the UART interface runs at a very different clock frequency than the display control, and it's not an integer multiple where you could easily kind of switch between the different clock domains. So why do we have 6 RAMs? Because we only have 3 colors. But remember, as Shahriar explained earlier, if you look at the interface to the LED matrix, actually we always write, first of all, we write red, green and blue in parallel, and we also write the top and the bottom half of the matrix in parallel. So meaning we actually need 6, we're gonna have 6 lines. So each line has a dedicated RAM inside the FPGA that holds the data that goes into that data line. That's why we are using 6 different RAMs, so we can read all of them in parallel. This is one of the big strengths of an FPGA implementation, that we can have each data line has its own dedicated logic. We don't have to share a pulse width modulation controller or anything like this. Each line has its dedicated lookup table for gamma correction. All of this happens in parallel inside the FPGA. That's why we can achieve the frame rate.
But 200, I think, right? We're hitting
close to 200 frames per second.
And if you look at the Arduino codes, for example, that are available to drive these screens, they actually write code at a very low level in assembly often, in order to be able to increase the timing margins and have a very efficient code that's really close to the hardware of the microcontroller, in order to be able to do this inside a typical microcontroller that you can buy, like an Arduino or so. But in reality, any serious display driver is of course never done directly in a microprocessor. It's always done either in this specific ASIC designed for driving displays, which would look something like this, or it would be done with an FPGA. This is why this approach is the better engineering solution for a scalable solution, as opposed to using like something like an Arduino.
To look in detail what happens inside the display control, I think the easiest is if we look at a simulation of the FPGA behavior, and look at how the different signals inside the FPGA actually change.
So as you know, because an FPGA code, like a VHDL code or a Verilog code, is a description of a hardware configuration. It's very different from sequential code that you write, for example, C or Java or something along those lines. It's not processed in the same way. It's a description. You're literally describing this as if you were drawing it in hardware, except you're using words in order to do that. That's how a VHDL or Verilog code, that's how an FPGA works. And because you're doing that, you have full simulation capability of that hardware, because every bit of hardware that's inside the FPGA is fully modeled, and therefore you can completely simulate it. So I guess what we can see is we should be able to see all of these red, green, blue, address, clock, and output enable, latch, the behavior, all of this through an entire frame can be simulated in an FPGA easily.
Yeah, that's easy to simulate, and what is very nice is that actually all that software is provided by the FPGA vendors. In our case, we're using a Xilinx FPGA, but there's also other vendors like Altera. All of them provide their software development environment for free, at least for the smaller devices that they sell. If you want to program something for a high-end device that costs a few $1,000s, then you also need to pay for the license to actually implement something on these devices.
Exactly. So let's now move on to the Xilinx FPGA software to briefly go over, just to get a feel of, without going into too much detail, just to get a feel of the VHDL code that was written, and especially look at the simulation, because we're going to go ahead and actually measure those waveforms directly on the board, and then you can see that they match the simulation. So let's move on to that piece of the software.
So this is the main window of that Xilinx software. They call it ISE Project Navigator, which is their main suite. They actually, for their newer FPGAs, they came up with a new software called Vivado, but we are using a Xilinx Spartan-6 where we use the ISE Project Navigator. So just to very briefly, I don't want to go into the details of the code. I think if anybody's interested, you'll be able to download all the source code from the Signal Path website. So feel free to take a look and play with it. Just briefly, here on the left is Prima our project view. You can see here, this is the top file of the FPGA code, and then you can see the major blocks that you also saw in the block diagram, which is a PLL, which is not described in VHDL, but which is kind of programmed through Xilinx specific user interface. And then we have the two main blocks, the Uart interface and the display controller. And then, well, we have one more block here, which we call animation, where we're just for testing the display. We are just changing the colors of the LEDs. And then there's one more file, which is a user constraint file that contains all the information about the hardware. This contains the information about the clock frequency, which signal is connected to which pin of the FPGA, what interface standard we are using, which is LVTTL logic. This kind of hardware information is not part of the VHDL code, but is part of a separate constraint file. I think that's all I'm going to say about the project navigator. Let's open the simulation and take a look how the waveforms look there. So this is how the user interface of the FPGA simulator looks like. And you can again see on the left side here we have our hierarchy of the FPGA with the different blocks. And we can actually, inside the simulator, we can load any signal internal of the FPGA. We can have it displayed in the display section here on the right. And what I've done is I've loaded all the signals that are part of the display controller. So you can see the top four signals, which are color coded in yellow. These are the inputs into the display controller. It's the clock coming from the PLL, a reset pin, and then a display enable pin, and of course the RAM that comes out of the FPGA. 48 bits, because it's remember it's red, green, blue twice because of the parallel lines. So it's 6 lines times 8 bit is 48 bits. Then the RAM address is the first output of our module. This is something that's connected internally inside the FPGA to the RAM, describing what address from the RAM we want to read. And then the remaining outputs from this block is the RGB lines. RGB1 and RGB2 are the 6 RGB lines that are connected to the LED matrix. Then the 4-bit display address, the display clock, the output enable, and the latch. All the other signals that you see here and that are color coded in blue, that's the internal signals inside the display controller. The most important one here being the state of the state machine that controls, as I explained before, the overall behavior and control of that display driver. So here in the right side we can see all the signals and what values they have at a specific time instance, and we display here like one full frame transmitted from the FPGA to the matrix, LED matrix. And you can see here the display address slowly increasing from 0 all the way to 15, meaning remember we are driving the top and bottom portion of the LED matrix in parallel, meaning if once the address counter reaches 15, we have written 32 lines in the matrix, and the frame is complete. And you can see writing one full frame takes roughly 5.64 milliseconds. So in 1 second we are roughly able to write close to 200 frames per second.
So let's talk a little bit about the PWM. Now obviously a lot happens while you're writing line 0, for example, here, or line 1 and line 2, because there's a lot of activity in between the different lines. And I guess that the reason for that is because you're doing PWM. So that means that you're doing your PWM display within each line as opposed to within each frame.
Yeah, so the way we achieve 8-bit of color, or 24-bit, 8-bit per color RGB, is that we turn the LEDs on only for a portion of the time, because the LED can either be on or off. There is no dimming function. So the way to dim the LEDs is actually to not have them on all the time, but to actually only have them on a portion of the time. And the port, or the granularity, is 256. So we can have them on 1/256 or 2/256 of the time duration that we drive one line, and that way we can achieve 256 different brightness levels per LED, and that gives us 8-bit of resolution in the brightness. And as we have 3 different colors, it's 24 bits total colors.
So if you go to the beginning and expand the graph a little bit.
So we can zoom in into the processing of one single line. Let's go to the beginning, or maybe actually let's go to the middle here, because there's actually some activity on the RGB lines. So now we can see here, this is the time duration it takes to write one line, and we can see that here the different LEDs are turned on or off for different amounts of time.
So each line you write 256 times.
Each line we write 256 times,
yeah.
And sometimes we write ones, which means the LED is on. Sometimes we write zeros.
And the human eye will see that as different brightness of the individual LEDs as you get a full frame eventually.
Exactly. So if we zoom in even further, now we start to see the display clock and the display latch starts to appear. So now we can see we are always writing, if you count here, this is 32 clock cycles, because one row has 32 LEDs, so we write 32 values. Each gets clocked in with the clock signal, and you can see the first maybe 7 or 8 pixels of the matrix are currently turned off of that row, and the remaining roughly 24 LEDs in that row are turned on. And once we've completely finished writing the data for that row into the LED matrix, we trigger the display latch, which loads that data into the actual kind of
the drivers, yeah.
LED drivers, and actually turns the LEDs on or off. Yeah, so if somebody of you is more interested to dig into this VHDL design deeper, maybe you want to reuse portions of the design for your own work, remember this. All the files are available. Also, the simulation files are available on the Signal Path website. So feel free to download them and run the simulation yourself. You can explore all the different signals, compare them against the VHDL code, and you can figure out the exact details. This is unfortunately too much to go through in a 1-hour video. This would just take already a couple of hours just for this VHDL design, which is probably not interesting for everybody. So whoever is interested, feel free to play with this. And if you have any questions, just shoot Shahriar an email. He can forward it to me, and I'll try to answer you.
Yeah,
if there's any questions.
You can leave comments on the YouTube channel, and we'll try and answer it. But what we've done here right now is that I have connected the FPGA board directly to the oscilloscope, so we can do this measurement very quickly on the oscilloscope, so that you can indeed see that this logic behavior that you can see from all the IOs going out of the FPGA into the RGB matrix is exactly like the FPGA simulation predicts. So let's take a step out of the computer and take a look at the setup and the logic analyzer that's running on the oscilloscope, and take a look at the waveforms. So here what I've done is I've taken the FPGA board that Timo has programmed and the waveforms that he just showed you and described to you. Now, instead of driving the display, here's the display cables. I've disconnected them completely, and I've connected a logic analyzer from my MSOS 804A to be able to monitor all the signals that are coming out of the FPGA directly onto the logic analyzer of the oscilloscope. And that would allow me to basically replicate what he had shown in the simulation portion that you just saw. So if I go ahead and take a look at the display, let me get this right in the frame for you, and guess what? We see exactly what Timo was talking about on the FPGA simulation software. I have put in the red, green, blue, the 6 lines, which are the RGB lines coming from the FPGA. You can see they're toggling quite a bit because I'm displaying the clock data, so they're random data being displayed there. You cannot discern them, but A0, A1, A2, and A3, which are the address bits, you can clearly see the address advancing, and I have defined a bus here showing the address going from 0, 1, 2, 3, 4, and 5. That's the different lines being written, and of course a whole lot is happening between each of the lines. All the PWM, all the output enable latch lines, and all the output enable bits that are triggering, they're all happening within there. So if I go ahead and zoom in here, eventually if I zoom sufficiently in, you can see the clock frequency right there. So here's the address changing, here's the clock frequency, 32 clock writing 32 pixels, another 32 clock writing another 32 pixels, and you can see all the data, the PWM data happening on the right. And I can continue to just go on and on and on, and you can see all the waveform. But this behavior is exactly the same as the behavior that we saw in the simulation on the FPGA. And you can see that at the 0 line, this is when the address changes is when the output line actually changes. In between the different lines, you don't need to disable the output. you want to keep it enabled because you want to have the line lit up. And you can go through this in more detail, of course, but I suggest, as Timo said, download the FPGA code, run the software, familiarize yourself. Being able to do this on FPGA is a huge asset to people who like to work on this type of stuff. So let's go ahead and take a look at the board a bit more. And of course, because we're loading frames, we have a capability of loading pictures onto it. Right now, as you turn on the device, it shows this start up the screen that Timo has programmed some random coloring and just making sure that all the pixels are on. This pattern that you see on video is because of the aliasing of the frames of the camera with respect to the nearly 200 frames per second of the display driver. That obviously we don't see that when we're looking at it. It's just the artifact of filming it. So Timo is going to run a code for us to show one picture that I have saved from before. Let's see through Bluetooth, and there it is. I'm sure you recognize this guy. And so because we are just loading 1024 pixel frames, you can load any image you want, and here's one example of it. So I think we've gone through quite a bit of information. Timo, anything else you want to add?
I think we pretty much covered most of the things. Yeah. If anybody still has questions, leave a comment.
Yeah, leave a comment, exactly. And
I'll try to answer it.
Yeah, just wanted to give you an idea of what this looks like. Obviously, there's a lot of detail that Timo didn't go through because it would have taken much longer. But don't forget to thank him in the comment section to give us his precious time to go through this for us. And like I said, it's pretty simple stuff for him, but there's a lot of learning experience for the rest of us. So Timo and I signing off, and hopefully we'll do more videos for us in the future for you to get it. Yeah.
I'll be happy. Let's see if we find another project to work on.
Fantastic. All right, guys. Until next time.
Bye.